All right, so today I'm gonna continue on talking about the GPU, and we'll wrap up uh, this topic by leaving you with some of the things that people have been doing, including myself, on the GPU architecture, and then we'll follow on based on how much time you have left. I'm gonna basically introduce the memory to you because basically that's now that we are at the point we cover everything that I would like to cover from the processor side. So you look at the motherboard, we cover everything that goes into the processing side, the CPU and the GPU, and then we're gonna talk about DRAM, which is the other important elements in your computer, aside from the hard drive and all those things that are peripherals and input outputs. Uh, Again, someone told me this morning that my microphone is bad. So if you cannot hear me or if I look like I'm talking, but you cannot hear what I say, please do let me know as soon as possible because I just don't want to speak without actually voice going through the video. Uh, so let's begin the lecture by going to, wait, I can't animate here. Click. All right. By going through some of the recaps of what we covered on Monday. So on Monday, we first talk about fundamental concepts behind what is a GPU and how the GPU works, right? The first thing that is the backbone of the GPU is called SIMD or SIMT, both of which are single instruction, multiple data or multiple threads. It means that I fetch one thing, one instruction, but that instruction operate on multiple pieces of data. Let's say you have a matrix, right? A matrix can be 64 by 64, and let's say you want to multiply another matrix, 64 by 64. By the way, if you do a matrix multiply, or you would call something a matrix multiply, the dimension should match. I've seen a student over here at TTS telling me he's doing a matrix multiply, but it's 5 by 5 versus 512 by 512. And I'm like, you can't do that multiply. It's just impossible. Yeah, math broke. Anyway, so with the 64 by 64 matrix, you want to multiply with another matrix. What do you have to do is basically a bunch of multiply on a lot of data, right? So the GPU would get that one multiply instruction and would actually specifically say, okay, I'm gonna take the first row, 64 elements, multiply by the other 64 elements in the column, do that multiply with one instruction. So you basically essentially do 64 multiply in one instruction. Believe it or not, this SIMD unit is also present on your CPU. So you can do this matrix multiply on the CPU, similarly to the GPU. How many of you heard about the SSE, Intel SSE technology? I guess not. It's a special part of the CPU that allows you to perform SIMD operation. Right? You fetch one instruction. That instruction essentially consists of operations on multiple pieces of the data. Right? So what you ended up doing is a bunch of multiply. The second concept behind the GPU is what we call fine-grained multi-threading. We covered this during a branch prediction, so I hope you remember that. If you don't remember what is fine-grained multi-threading, basically you switch to another thread every single cycle so that you have something to put in the pipeline. The last thing you have to do on a GPU is something closely resemble predicated execution. This is to handle branches. I'm going to give you the recap of that. Then one thing I want to make sure you are aware is inside the GPU, once you have the program that you can run on a GPU, if you have write the TensorFlow code or PyTorch, right? Eventually, this becomes CUDA code that running basically runnable on the GPU side. They will be dispatched to the GPU in multiple thread blocks, or what sometimes the software folks call it the grid. Within the grid, there's also another subunit called a warp. And then each of these boxes is one thread that operates on a single piece of data in a instruction. Then the GPU core, or what NVIDIA is calling simultaneous multiprocessor, or SM, will handle each of the thread blocks. Each of the core will have a bunch of execution unit, or the ALUs. So in contrast from what the CPU has, the GPU will have a lot more ALU. It will send a warp, as I show here, to the execution unit, so you can execute everything in that warp in one cycle. So this is how the GPU works, and all the thread blocks from your program will be distributed across all GPU core. A quick thing, as I said last Monday, basically CUDA core, which is what NVIDIA claimed, is not a real actual processing core. CUDA core is one ALU. So don't just look at the number of CUDA core and tell people that, hey, there are 2,000 GPU core. No, that's not true. So let's go back to our friendly 5-stage pipeline, which you are all working on. You have fetch, decode, execute, memory, and write back, right? And then for the past lectures, we've been talking about multiple techniques on the CPU to make the CPU fast. You have instruction cache, you obviously have decoder and the ALU, you have the load store unit to handle memory operations, you have the write back phase where you can basically commit to writing the register files that the programmer can see. Then you have the branch predictor. You have whatever is needed for the out of order execution depending on the technology. So you have instruction scheduling logic, the reservation station, future files. These are more another copy of the register files. You have the SRAM cache. You have the architectural register files. All these things are added to make single thread performance really good, right? So if you run something on the CPU, the performance of that thread is really good. On a GPU, fundamentally, right, to run an instruction, you don't need these fancy things. So the GPU designer came up with an idea of, let's remove a bunch of these things. No branch predictor, no future file, just leave me with register files. No logic for the out of order scheduling. I'm gonna add a lot more ALU because I know that I'm gonna do the same instruction but over and over and over again on multiple pieces of data. So I'm gonna add a lot of ALUs. I'm gonna increase the size of register files so that I can support multiple data that are going on at once. I'm gonna have this much smaller cache, right? Data cache that are much smaller. And some of the data cache can be software managed. They make some assumption that the folks who can run the GPU or basically write GPU code knows about their application enough that they can manage their own cache. They can tell, okay, this data should be in the cache. At some point in this function, kick this data out from the cache. So many of these things are added. Instead of single thread performance, they're being added for instruction throughput. You want to be able to process many instructions at the same time. And the way GPU deal with stall, this is from Monday lecture. So let's look at this GPU core or SM. Now that you have multiple warp on the core, right? The way it works is that each instant of time, the core will pick one of these warp, issue them to the pipeline. The next cycle, it would pick the next warp, put them in the pipeline so that each time you iterate through the warps, something else is being pushed into the pipeline. And if you have load and store instruction, which is actually now the focus of this lecture, in this case, warp A will actually, because there are 8 threads, they point to the same instruction. So they're issuing is a one load, is 8 loads on 8 different pieces of data, right? And because 8 loads would take a while, so it would now, the GPU would pick these 3 warps to rotate in. And at some point, let's assume that you have a bunch of load instruction on all the warps. what will you ended up doing is you now issue 32 different loads. GPU core say, okay, I ran out of things to run. Nothing can be pushed on a pipeline. I'm going to stall until some of the data come back. Now I can become active and run something again, right? And we talk about one of the issue that GPU can run into. Let's say you do ray tracing, which actually consists of multiple if-else statements. And over here, I look at one warp. The result of this if-else, this if A equals 0 is true, true, false, false, true, false, false, false on these 8 threads, right? What you need to do is for the blue box threads that are true, these blue things, so I'm going to change the ink color to blue. These blue things have to run this part of the code, while the red things has to run this part of the code, right? So the way it works is GPU would mark out the false part so that all the true threads execute the true portion. Then would mask out the true part of the threads, allowing the false part to run the do something else part. This issue decrease how many of these ALUs are active at the same time, right? Over here, in the if case, only 3 threads are active. The other 5 threads are like, I'm not doing anything. For the else part, the false part are active. I'm doing something, but the true threads are not doing anything. This issue is called branch divergence. So this basically lower GPU performance. If you blindly write code in GPU in CUDA and you expect a good performance, and when you actually run it and it's not really performing as fast as you think, this might be one of the reasons why. Right? And we show this example from the last lecture. If you have any question on this, let me know. I'm gonna cover this during the office hour. On next Monday, actually, tomorrow I'm actually take a brief vacation, so I can be in the office hour, but I might not be in front of the desktop. So now that I recap whatever we went through on Monday, I'm gonna move on to how to handle memory accesses on the GPU first. This is going to cover the caching side, not about the memory yet, but let's cover the caching side. Any questions so far before I move into caching on the GPU? All right, so let's talk about how the GPU handle data access. It's essentially similar to the CPU. GPU also have things like load store unit, the cache, and the memory hierarchy, right? Right now, the simple version of the GPU, the one that we buy, the one that we have the money we can buy, it doesn't really support a full-blown CPU like virtual memory as we know it. Even the A100, that is the most expensive model, they still don't support virtual memory as we know it. Similar to the CPU, it's still not like fully featured like a CPU side. The reason why that is the case, the GPU does not have an OS. It relies on the driver from the CPU side to handle memory locations. This doesn't really mean you don't get the typical virtual memory benefits. But there are things that you cannot do. You don't really fully get memory protection as fine-grained as the CPU counterparts. There are some limited form of memory protection. There's no illusion of large memory. There's some illusion of you can extend your memory to the CPU, and that's pretty much it. But then if you extend the memory to the CPU, the performance sucks. I'm gonna tell you how bad it is in a bit. You get an illusion of contiguous single address space, so you don't have to worry about where my data is. Earlier model of the GPU, you do have to worry about where your data is. There's no virtual memory. You kind of have to deal with it and that's a pain. These days better. And from the older generation onward, NVIDIA did a better job at like manage your virtual memory. It's still not as fully featured, as I said, compared to CPU counterparts. And these are information that at least I gather from reading papers and talking to people in the industry as well as academia. And this is one of my thesis, like a part of my thesis on this topic. So I hope you can believe that these are true. But if you want to access a cache in the CPU on the time, if you look at the timeline, and for some reason there's red ink over here, so let me erase this. So if you look at the time, and you have load A and load B, right? This is the CPU side, the one we know so far since the file processing class and system skill class. You have two loads from the CPU. I want to get my data. Let's say load A is a cache miss, load B is a cache hit. The cache hit would get the data first because they're fast. The cache miss would have to go to DRAM, right, to get the data from the main memory, and that is going to take more time. Something as simple as that. The stall time of A, you need to stall for this much to get your data. For load B, you only have to stall for this much to get your data. You see the difference, right? That's why when you program, you want to make sure your data stays in the cache. The benefit of the cache here is memory accesses are much, much, much faster. Let's look about caching in GPU. Let's say I have a warp. The red things are cache miss. The blue things are cache hits. They are at the same instruction. They want to load some data onto your pointer address or whatever, right? You want to load some data from these addresses. If you look at the time, what will happen to the blue things? If I issue a cache hit request, it's going to get the data first, right? Any questions so far? It will get the data to the blue, not the blue, the green boxes will get the data first. Any question here so far? Then the red box, which gets the data from the main memory, will take the data from the main memory. So my question is this: if I look at warp A, when is the next time warp A is available that I can send the next instruction into the pipeline? Is it at point 1 or point number 2 that I label here? Time point 1 or time point 2? Anyone think about it a little bit? If I have warp A that behaves like this, yes, it's point number 2. That's when I can issue the next instruction. This is the big difference. In CPU case, it's time point 1 because you're looking at one thing, one thread. Over here, you look at all these 8 threads in parallel. So you need to wait for the slowest thread to get the data until I can resume my instruction, right? So the stall time of warp A is at point number 2. So moving data, okay. So any questions so far about this? And accessing a cache in the GPU, you have to wait for a long time. If you have a cache miss, there's still a benefit of using the cache. But there's some caveat, right? There's some caveat that comes with it. The next issue is, now that we know how caching works on the GPU, and that's a key difference, GPU is like a slave to the CPU. Okay, I used that word, and I've heard that you're not supposed to use this word. What's a new word? I forgot. What's the new word for master slave? Anyone know? Otherwise, I'm gonna keep using this word until I'm done with this lecture, and you need to go and Google that word. Sorry. I think manager and worker. Okay. All right. So GPU is like a worker to the CPU, like manager and worker. CPU is a host. right? It sends the data to the GPU. Basically, the way you launch the GPU, what we call compute kernel, or we call GPU kernel. GPU kernel is basically a piece of code that are written in CUDA language to say, okay, this part of the code should be run on a GPU. Basically, you have the CPU, you have the GPU, you have the CPU memory, and you have the GPU memory. This is separated by your friendly PCIe interface. That big, long interface thing that you plug your graphic card into, that's where you transfer the data over back and forth between the two memory. The two memory here, right? When you issue the compute kernel or the GPU kernel, you send the kernel to the GPU. The CPU send the kernel like this to the CPU. Where do you store your code? Recap. Where do you store your code? In the memory, right? So the kernel code is stored here. Then it tells here are the data that you want to compute on. Get copy over here. So this is kernel code. Get copy over here. So basically, the CPU copy the code, copy the data over, and then say launch. Launch means the GPU would trigger and say, hey, I'm going to start running. I'm going to start running at this PC. It would run this code, and it would take the data that's being copied over here. Your GPU acts like a device. It takes the CPU's command and executes the code based on the command. So if you are running things on, say, TensorFlow or PyTorch or CUDA through CUDA Blast, or if you are hardcore and you want to write your own CUDA code, the way it works is the CPU, because it has its own DRAM, the GPU also has its own DRAM, which are a lot higher in bandwidth. These DRAM are connected to, as I said earlier, PCIe, or these days if you have a really high-end GPU, if you're rich and want to buy a big, huge GPU, they are connected to a faster interface called NVLink. These things are a lot slower than the bus between the last level cache and DRAM, right? So the way it works is the requirement success. If you want to run something on the GPU, the data has to be on the GPU side before you can run it. If you finish the execution on the GPU, you need to copy the data back before you run it. They share the data. The pointer, when you write the program, the pointer is shared. You just say launch, and that pointer would be assumed the data is now arriving at the GPU side. You have the explicit memory management, which means that you need to manually control all the memory copy. This is one of the overhead that you need to do as a programmer. You need to tell, okay, not just malloc. So how many people here hate malloc? And free, I guess, malloc and free. Or the fact that you forgot to free or you forgot to malloc. In C code? Yes, no? No opinion on that? Okay. So if you hate malloc, when you write GPU code, you not just have to do malloc, but you have to do copy. You CUDA malloc, then CUDA mem copy from host to device to copy from CPU to the GPU. Then you run. Then you do CUDA mem copy from device to host to copy the data back, then free the GPU memory, not freeing the pointer on the CPU side. These has to be manually controlled. To get performance, a lot of time you need to minimize data transfer. This is one of the big bottleneck inside the uh, basically GPU programming. A lot of people forgot about the fact that if you use more memory than the GPU provide, it's not just slow, it will basically the kernel might crash. I ran into that when I'm testing some of the programs just to test the point that it actually crashed, and it does. Right? The GPU doesn't really manage memory as fluidly as the CPU side. So the reason behind that is it doesn't really have the OS code to support every single thing. This is the beauty of having a really complex operating systems on the CPU side, right? When you're running Linux, when you're running Windows, if you run out of memory, it won't just reboot ahead, like go ahead and reboot. It would just become slow and try to manage the memory so that you don't feel the slowness. On a GPU, it's not the case. So a typical GPU operation, now I'm going to have a diagram. The left side is a CPU chip. The right side is a GPU card that you plug it in. The whole thing is a GPU card which has the DRAM on the card. So when you buy a GPU, DRAM comes with it. They actually solder the pins, right? The pins that connects the CPU, RAM, and motherboard that actually are being soldered onto the GPU board. Uh, First, you have to do CUDA malloc. It's a function called similar to malloc, but it allocates the space on the GPU memory, as I show here in this bluish, I think it's purple, blue purple color on the GPU memory. Then you need to perform CUDA memcopy, right? CUDA memcopy from the CPU, which is the host, to the GPU, which is the device, which I show here in this green box, which get copied to the allocated space on the GPU. Then you launch the kernel. Once you finish, then you need to copy the data back. Now the finished data is in green. This data get copied back to the CPU side, so the CPU can resume the execution and run whatever it wants to run. Any question about the typical operation before we cover this unified virtual memory concept? So in the unified memory, this is a newer technology. It's been out there for a few years, actually, like 5 years, I think. Basically, this technology allows you to create the illusion that the two memory are under the same address space. So you share the pointer. So instead of CUDA malloc followed by CUDA memcopy, what you need to do is called CUDA malloc manage. In this case, it utilizes this unified virtual memory technology, and then you don't have to manually copy the data. The GPU driver would predict when you have to copy the data and transfer the data automatically through demand paging. Demand paging is from our virtual memory lecture. Basically, when you have a fault, which is I need this pointer, but the pointer is not in the memory, which in this case not in the GPU memory, I'm going to bring the data over from a CPU. The problem here is this. This is connected through PCIe, so if you have the demand paging, it's going to be slow. So you lose the performance benefit through UVM if your data is bigger than GPU memory, because you need to manage the data between back and forth between the CPU and GPU memory. So the benefit on paper, this is good. It should make GPU simpler to program. The problem is that you cannot really predict sometimes when to transfer the data. Sometimes when you have multiple applications that are running on the GPU, sometimes you actually launch 2 or 4 kernels at the same time on the GPU. They share the memory. So the pages from one application can kick out someone else's pages. You can actually run into lower performance. So making UVM works well is still a really active research area. And if you're interested in this, let me know. I've been active in this area. I've been publishing a few papers, one in 2018 and one in 19, and then right now I'm working with like university in Korea to basically improve the performance of UVM. So if you're interested in this for your senior project or something, let me know. I have multiple smaller tasks that you can try out and learn more how GPU driver works or how the GPU programming works. Then, because a lot of people talk about TensorFlow, right? So I'm going to talk a little bit about systolic arrays or the idea behind the tensor core that comes from the technology. This is adopted at Google. They have a huge machine that can run machine learning based application. The concept behind systolic array, and by the way, this will not go into your exam. Anything from this point on will not go into your exam. Clear? I just want to give you some historical concepts that it's been there for a while and it's been popularized these days because you want to improve performance. This thing called systolic arrays are something like this. So instead of having the CPU and the memory, which is the top part right here, right? This is the CPU, this is DRAM. A lot of time when you compute something, you generate the data for the next instruction, right? You generate the data for the next instruction. So H.T. Kung, back in 1982, proposed this idea of, well, if the processing elements generate the data for the next processing elements, which then generate the data again, right, for the next processing elements. Why don't I just do this? I will connect the first processing element, generate the data for a second processing element. The second processing element generate the data to the third processing element, so on and so forth. So it basically you generate the new piece of data without going to the main memory, right? So you keep doing this until you finish. Then you only write to the memory only once when you finish computing. What is the use of this? How many of you have to do convolution through one of those like CNN before? Okay. Do you know what convolution is? Awesome. So if you were in deep learning topic, basic convolution is you have two functions and you think of two functions like a train, I guess. So they face each other and when they collide, you multiply them together. Cool. The operation is simple, multiply and add. So from the same concept, actually from the same paper that I showed earlier, this 1982 paper, the design that I showed right here is how can you make the convolution through these processing elements. The processing elements take the two functions value, it has the weight that's already built in, multiply them together, yay, and then you get the output. And you can do convolution this way, right? Without going to the main memory, How about FFT? FFT is common not in deep learning, but now in image processing and anything related to signal processing. Signal that can range from music, acoustic application, communication that you need to like send those like 5G signal to different places, or image processing. These are 2D signals, right? FFT allows you to convert your data into the frequency domain from the time domain to frequency domain. So a lot of operations become cheaper. You don't have to do integrate. So if you have to integrate in the time domain, that is converted in to multiply in the frequency domain. So you can use the systolic array to do FFT. So this concept is now using the same concept, you can build a matrix multiply. And tensor cores basic a huge convolution and matrix multiply, right? And as you can imagine, if you don't have to go to the memory, which is the slow part of your processing element, you can actually improve the performance quite a lot this way. Let me show you one more example that we propose. So do you see my screen? That is a paper. We just published this, what is it? This month, basically. So if you look at this, we are doing DNA sequencing. And here, this part, this is systolic arrays that we use to move data really quickly between different processing elements. You see PE, right? Processing elements. So you bring the DNA sequence, basically all the pattern ACTG in a long string of those letters, feed it to the processing elements to process so that you can do string matching and compare. Basically, literally what you have to do is here, you have a reference genome and you want to compare whatever you detect and compare it against the reference genome so you know the location of those genes. Right? Basically, so that you can detect things like there any insertion, deletion, substitution. Are you likely to get certain cancer? Are you likely to get certain illness based on your gene? So these has a lot of application. All right, so that's it for the systolic array. Any questions about this? Again, not going to go to your exam. The next thing is not going to go to your exam as well. But now that I kind of cover what I want to cover for the GPU side, I want to tell you what else can we do, right? So this is going to be a recap. What's a day in life when I have a data access? This is almost a recap of the ending of our caching lecture. Right? You have a load at address, I don't know, 0x80 to 0. This is what we want to do. What will happen is this load will go to the cache, right? Then L2 cache. Then the main memory. And if you have virtual memory, what you have to do is also this load is a virtual address, so it has to go to the TLB structure. If you don't have the data in the TLB, what do you have to do? Quick recap, what do you have to do if you have a TLB miss? This is a good reviewing part. Okay, if I have a TLB miss, what's the next thing I have to do to get my physical address? What's that process called? It's called a page walk. You go to the page table, get the data back, walk it again. This is basically 4 trips to the page table until you got your physical address to access the cache so that you can get your data, right? So this is kind of like a day in life of a data access, which is inefficient. And it's even worse, as I showed earlier, with the GPU. Why is it the case? If you look at this, the cache does not really provide the fast access to your data, right? So there's a work that I published in 2015 basically question this, like basically, how do I take a full advantage of this fast cache, right, on a GPU? So what we found through a bunch, like running a bunch of GPGPU application is something like this. There's quite a lot of WAPs that has thread that looks like this. Also, there's quite a lot of WAP that has thread that look like this as well. only one cache miss. The other warp only have one cache hit. How long do they have to wait until I can run the next instruction for each of these two warps? How long do I have to wait? To the main memory. But basically, if you look at this, they both have to wait roughly equally long, right? So the goal of our work is we want to convert this mostly hit warp into everything is a cache hit, which means that you can then take advantage of the cache, and then for those that only have one or two cache hits, just kick that cache block out of the cache. Why are you wasting the cache space, right? So you want to convert this to almost cache, basically warp type, right? Where everything go to the main memory, because I don't care. I already send requests 7 requests to the main memory. I sending one more request doesn't matter. In reality, you're not looking at 8 guts. Typical swap size is between 32 to 64, right? So if you send 63 requests versus 64 requests, or 60 requests versus 64 requests to DRAM, it doesn't matter. It will take a long time. It is much better to yield this cache space to the warp that only have one or two cache lists. So in all, or in all, basically this allows you to get your data back quickly and finally take advantage of the cache. So this is the work done in collaboration with AMD Research, and this is done when I was at CMU, along with also folks at Penn State as well. It's published in PAC 2024. Basically, we try to do whatever I just explained, and we show that, hey, we can improve performance that way, right? So this is one of the possible bottleneck on GPU application. We get about 20% better performance because we do perform better. Actually, as a side effect, you lower the energy compared to best previous work on this topic. And how about branch divergence, right? Branch divergence, there are actually a lot of ideas being proposed because it's another significant problem. They're being solved to some extent around like year 2010 to 2013, 14. The key idea is you can switch as Champ mentioned last class on Monday. This is basically the idea they're proposing. If you have threads in two warps, and you know that some of them are going to the true part, some of them going to the false part, why don't you just mix them so that the warp has threads that go to the same path in one warp, threads that go to a different path in another warp, right? So that way they all go into the same direction. And the requirement that you have to do is you need to manage how you use the register files a little bit, because remember the lane that we mentioned, the execution unit that has the first, second thing, the first, second, third thing for the thread in a warp. They have to stay on the same lane because the register files is tied to the lane. So if you switch to a different lane, you lose all your data. So when you switch from warp A to warp B, if you're in lane number 3, you need to stay in lane number 3 in warp B. There are some follow-up works that talks about additional hardware overhead to reduce these requirements. Now you can switch in a more complex way and reduce the branch divergence problem on GPU. If you're interested in this direction, also feel free to let me know, but I need to warn you that it's a older problem. So there might not be like as much novelty compared to like you're looking at how you manage the memory on the GPU. And we talk about the memory, right? So before we move on from the GPU topic, any questions before we take a quick break and we'll talk about DRAM? All right, so if you might have any questions about the GPU, feel free to type it in. Otherwise, let's take a quick break 10 minutes. We'll meet back at 1:05. Is that okay? All right. So we will come back and resume talking about DRAM, and we will discuss a few things that you might have heard when you buy a computer that might be recommended by the seller whenever you go to the IT store. I'll explain why that is the case, so you know the concept behind it. All right, so we'll meet again in 10 minutes. I'm gonna go make some coffee and get some water. See you all in 10 minutes. All right, so I assume that most of you are back, if not all. So let me continue on to DRAM. Before we begin, let's talk quickly about what happened when you have the last level cache. LLC stands for last level cache. The data request, which at that point is the physical address, that data request, you need to find the data in the main memory, right? So similar to SRAM caches, DRAM has limited capacity and bandwidth. So what do I mean exactly by limited bandwidth? We'll talk about this in the current lecture and going into Monday. Uh, the capacity point of view is pretty obvious. Basically, if you buy a 12 gigabyte DRAM, you cannot use more than 12 gigabytes. If you use 32 gigabyte of DRAM in the system, you can't use more than 32 gigabytes. There are a lot of work that goes into how to pack more capacitor so that one DRAM can contain more data. In terms of bandwidth, it's still similar to capacity, but we'll discuss about the certain things on what govern that bandwidth. But before we go into that, let me introduce one more structure right in the cache. This is called the MSHR, Miss Status Handling Register. It's a register that is used to handle cache misses, right? So let's say you have cache miss to the same block. The question I need to ask you is, should I send more data requests, or should I just wait for that ongoing cache miss to get my cache block, right? Do I issue another request? The better question is, how should the cache handle cache miss? The solution comes into this form of register. Basically, the MSHR will work like this. When you have a cache miss, you store all the miss related information, something like the address of the miss, who requested this, right? Who requests this? Is it processor 1, processor 2, if it's multi-core, right? Is it core 1, core 2, core 3, or core 4, right? And those information will be used to make sure you don't send so many cache miss requests to DRAM to get your data. Why do you need this? So that first of all, you know who demands the data. Once you have the data back, you know, okay, I will have to send this data to processor 1 pipeline. I have to send this data to processor 3's pipeline. So that you know on like all the ongoing misses that are being resolved right now. Why is this useful? Let's say I have cache miss to address 0x80, and I have another access from this processor 1. Then processor 3 say, I want 0x80 as well. What does this mean? What does this mean when I have processor 1 and processor 3 comes at the two different time that wants the same data? They share that address, right? And what one thing we can do is, well, processor 1's request come first. I'm waiting for the data. I have processor 3's request coming in and say, hey, I want that same address. Instead of sending the same request again to DRAM, processor C3 request wait in this MSHR, wait for the processor 1's data request. Once you have that cache block, everyone gets the data. This eliminates redundant work that you have to do, right? You don't have to send multiple requests to get the same data again and again and again in a short period of time. And the number of these MSHR entries, it limits the number of in-flight DRAM requests. Anyone want to guess why? My hint is that every single request has to be allocated first in the MSHR. So the number of MSHR entries limit all possible in-flight DRAM requests. Anyone want to guess why is that? So let's say I have 32 MHHR entry in my system. How many ongoing DRAM requests I can issue at the same time? If I have 32 MHHR requests. I will be able to issue up to 32 requests, right? Because if I have a cache miss, I first need to allocate an entry in MHHR. If I ran out of that entry, I cannot allocate that entry. I have to wait. So I can only issue up to 32 VRAM requests. So now that we talk about MSHR, hopefully you guys are back because it's been 112 and it's been awfully quiet. But let's talk about DRAM. Are you back? Anyone here? Yes, no? Just type something in if you're here. Okay, thank you. I just want to make sure now that we are talking about DRAM. So DRAM, the unit, that DRAM stick that we buy, I'm not sure how we call that in Thai. I'm not even sure how a lot of people call it in English, actually. Like a unit of DRAM that you buy, that stick thing. The official name is DIMM. DIMM, Dual Inline Memory Module. The DRAM DIMM is connected to the processor side through the memory controller. I'm not going to enforce you to call it DRAM DIMM, but I just want to make sure whenever I say the word DRAM DIMM, you know what I mean. Because I'm so used to that word. And if I say DRAM DIMM, you know what I'm talking about. It's that memory stick that you buy. The DRAM DIMM is broken down into multiple units, from large to small, right? The smallest unit is the cell. This is 1 bit of data, right? Then multiple cells is grouped into a row. A row of data is about 4 kilobytes, 2 kilobytes, depending on the configuration. The DRAM specification will actually tell how big is one DRAM row. Then multiple cells that are grouped together is going to be in a 2D matrix, like a kind of organization. Each one of these things will be grouped into a unit called a DRAM bank. Multiple banks work together in a DRAM rank, and then each DIMM is it can be plugged into your motherboard and it connects to what we call DRAM channel. DIMM stands for Dual Inline Memory Module. And during each time interval, everything is in a digital world, right? A digital world, the main meaning of a digital world is everything goes according to the clock signal. The clock is going to look like this. Up, down, up, down, up, down, up, down, up, down. This is one cycle. In one cycle, you can do one thing, right? So during each time interval, DRAM will use the bus between DRAM and the CPU to transfer some amount of data. So hopefully this addressed Brandon's question back, I think Wednesday, right? I think the question was last Wednesday about the bus between the cache and DRAM and how there might be multiple buses. There are n number of buses based on number of channel. So these channel determine how many buses you can have between your DRAM and your processor. And each clock cycle, you can send a certain amount of data over from the memory to the processor. Because the memory access take a long time to access, one thing we can do is, well, we can send a bunch of accesses in parallel from the CPU. Right? This is doable. DRAM structure is actually designed to provide this. This is where you get the bandwidth from. In one cycle, they are not only sending one request data back, they're trying to send multiple request data back. A high-level overview of DRAM is like this. You buy the DRAM DIMM, right? The memory stick that you buy that costs about 2,000 baht. Each one of these DIMM is connected to a processor through memory channel. How many of you buy a motherboard and saw that they have, let's say if there are 4 DRAM slots, they have different color? How many of you notice that they have different color? Let me get you a picture so it's more clear on what I mean. Okay, so you've seen it, but you don't know why. So now we will tell you why. But let me first get the picture. All right, do you see this picture? And you see my mouse? That's black and that's yellow. Black and yellow color. You see that? Each color belongs to one channel. The channel that we have, so can I close down the Google Chrome? You all see the black and yellow thing, right? This is where you plug in DRAM. You plug DRAM you can plug it into the black slot here, the yellow slot here, the black slot here, and the yellow slot here. There are 4 slots, 2 color. These means that there are 2 channels. Each of the color here is 1 channel, right? Color number 1, color number 2. To double check, if you read the motherboard manuals, they will say these are different DRAM channel. These are actual physical bus that connects. Basically, this physical bus are wiring. The wiring from your DRAM all the way to the CPU. So let's say you buy 2 sticks of DRAM and you happen to plug it in both of them in the black thing. What will happen? If you plug it into the black slots on both of them, are you plugging them all into one channel or all into 2 different channels? So let me ask you that first question. Same channel, right? So you plug them both in the same channel. It means that you have this wiring that you're not using, right? You lose half the bandwidth. Basically, you lose half the possible bandwidth because you plug both of them into one channel. This channel is a biggest unit of control that you have. Each one of them has a controller. Each one of them has its own data bus. Each one of them has its own command bus, data bus, and the bus that you can send the address into. So you can work these 2 channels in parallel, right? So if you buy 2 DRAM sticks and plug them by accident into the same color, you are basically squeezing all your requests through one channel. Just double check with the motherboard manual. Sometimes they say one color mean channel 1 and channel 2. Sometimes one color mean one channel. Double check that. I'm not sure when this changed. I'm not sure if it ever changed, but to be safe, make sure you plug them into 2 different channels to make the most use of your motherboard. You buy the motherboard, make sure you get out all the bandwidth that they give it to you. Any question on why do you want to plug your DRAM into multiple channels? All right. The next quick thing that I want to let you know when you buy a computer and you buy multiple DRAMs. Let's say you buy 4 of them. It just happened that 2 of them is the fast DRAM, 2 of them is slow DRAM because you run out of money and it's like, okay, fine, I need more DRAM, but I'm gonna buy the slow one. Make sure the same speed is plugged into the same channel because each one of these channel has one controller, so they will be configured to the slowest DRAM getting plugged on that channel. So if you have DRAM that is 2 speed, put the same speed into one channel, put a different speed into another. Otherwise, you're gonna end up with slow DRAM, right? So that's a high-level overview of DRAM. We'll go into the detail. Any questions so far? All right, so we'll start zooming into DRAM. If you look at both front and back of your DRAM, you notice that this black thing. Any questions so far? You see that there's a black chip plugged onto the DRAM, right? Those chips are actually where you store the data. That's where your data resides in, right? The green things are the substrate that connects everything together. The chip is where you store the data. You notice it's the front and the back side, right? If you buy a DRAM, you flip front and back. There'll be a black chip on both sides. The front side is rank 0. The back side is rank 1. There are different rank. And then each one of these are DRAM chips. Each one of them are DRAM chip. They work independently to some extent. The front side would work together to send the data from the front side's DRAM. The back side will also work together to send the data through the back side of DRAM. They all go to the pins that connects the DRAM to your motherboard. If you zoom into the chip, one thing that you see is that there will be broken down into multiple banks. These banks operate independently. Okay, channel speed is minimum DRAM to 1 speed. Yes. So if you plug two DRAM into the channel and it just happen to have different clock speed, they'll pick the slowest one. The reason why they pick the slowest one is if you pick the faster one, it means that the clock will be too fast for the slow one. Right? It will be too fast for the slow one. So within one cycle, the slow one would be like, wait, I haven't finished reading the data yet, but you go to the next cycle, I don't know what to do, so I can't operate. You will then need to make sure the speed match the slowest DRAM you plug in that channel. Does it answer your question? Okay. So yeah, when you buy DRAM, make sure you're aware of that. Otherwise, you're throwing money into something that you're not getting benefit. And these are never explained for some reason. Actually, even in the United States, right, in the most colleges, it just happened that my research group back at CMU, my advisors group, works like his work is primarily on DRAM. He has is one of leading researcher on memory technology. So he knows about this thing. And I'm like, why can't we just tell people to buy the correct things? And this is what I'm trying to do here. Inside DRAM, these banks work independently. So you can send requests to bank 0, request 1 here, and at the same time, request number 2 that goes to bank 2 and request number 3 that are inside bank 5 can be serviced in parallel, right? So what you want to do here is to make sure you send all your data requests to all these banks so that you can get all your data in parallel at the same time. If you have 8 requests through all 8 banks, you get all those 8 accesses at once. It might take a long time. It might take 50 nanoseconds, but then within that 50 nanoseconds, you get 8 of them. You finish 8 requests, right? Then you see there are 8 chips on DRAM. If you look at the picture of DRAM, I'm going to show you quickly here. There are 8 chips, right? Something like this. Or this. Or 16. DDR4. This is a much bigger DRAM. So you notice multiple chips on here. These 8 chips are designed to work together. The request 1, 2, and 3 that I draw here, they all go into all the 8 chips. Each chip, how big is your data cache? I mean, how big is your cache block? What we cover in caching lecture. It is 64 bytes, right? You get one cache block. So in theory, you're supposed to send all the 64 bytes. through multiple cycles, you should get 64 bytes of data, right? It means that each of these each of these wires coming from different chip will give you 8 bytes of data. This is through multiple cycles. Usually, this will be done through multiple cycles, but eventually all the chip will contribute to 1/8 of the processor. It depends on the number of chips. So you have more chips. It means that each chip will contribute less, but altogether you'll get a cache line. Any questions so far? All right. So with without any more questions, if you have questions, let me know anytime. I'll just answer them as time goes on. DRAM channel, as I said, it's a physically connected unit that connect right to the processor. It has its own data command and address buses. One channel is physically independent from other channels. It means that if I'm servicing request 1, 2, 3, 4, 5 on one channel, I can service request 7, 8, 9, 10 into another channel. You get both sides of the channels, you get more bandwidth, you double the bandwidth. Each channel has its own memory controller. We will talk about what is memory controller in a bit. This controller sends a series of DRAM commands, such as read this data from this address, make sure this data is ready to be read, make sure this data is written back to DRAM cells, make sure you can issue as many data read and write as possible. Inside the DRAM ranks, each individual rank contains multiple chips, as I said earlier. They work together as a rank to send or retrieve data from the chip. One thing that I want you to know is DRAM clock is actually slower than a CPU clock. Multiple ranks utilize the bus while the other rank is busy. This is fundamental concept behind dual inline memory module. And what I mean by this sentence is this. If you look at the clock that looks like this, right? And this is one cycle of DRAM clock. What will happen is because you have so if you look at DRAM, right? If you look at DRAM, this green thing here, and you have multiple chips, right? You have rank 0 and rank 1, right? Rank 0 and rank 1, the front and the back side. What the DRAM is doing is in this first half of the clock, you are sending rank 0's data, while the other half of the clock, you are sending rank 1's data. So within one clock cycle, you manage to squeeze in both ranks data. The clock cycle, when you look at DRAM, whatever they say, let's say it says 2666 megahertz. In reality, it's actually 1333 megahertz. But because you do dual inline, right? Dual inline, these double 2x bandwidth. So they can claim that within one cycle, you can send both ranks data, so it will behave as if you have 2666 megahertz clock. Any questions about the DRAM rank and why they can send data in both edge of your cycle? All right, so let's go to DRAM bank. DRAM bank is inside the chip. Data also distributed across all the DRAM banks. they can transfer your data in parallel. This is giving you what we call memory level parallelism. That's a share command bus where it only sends one command at a time. Right? The memory controller is responsible to send out these commands. Any questions before we go to the memory controller? All right. So I'm gonna keep going until we are at around like 150. I'm not sure if we managed to finish the memory controller, but if we do not, we'll do a recap on Monday. I went faster than I expected. I was planning to just finish like the earlier part and then talk about the memory controller next week. It turns out that we have about almost half an hour. So let's keep going. Now that we know about this bank level parallelism, which means that you can send multiple requests to multiple banks and they'll be serviced in parallel, which is a good thing. We need to look into this unit called a DRAM row. Inside the DRAM structure, charges are stored in DRAM cells that are too small to be sensed. These cells store few like less than 10 electrons, right? Inside those capacitor is only a few electrons in there. So the charge need to be amplified. What is an amplifier? Anyone use an amplifier when you guys listen to music or when you play a guitar or anything? Anyone use an amplifier before? Yes, no? Anyone use an amplifier before in life? Okay, so what do they do? Yes, in your headphone app. So what's the general thing that they do? Next is sound louder. Yes. Basically increase the amplitude, right? Increase the amplitude of your signal. Over here it's the same purpose. You need to amplify from a few electrons into another unit that contain more electrons. So you can sense, is this greater than certain value or is this lower than certain value? So that you can tell, is this a one or a zero, right? These unit of series of amplifier, this series of amplifier is called a row buffer. Recall that we have a row of DRAM. Basically, inside DRAM is structured like this. It basically is just a 2D array of capacitor, right? Inside this, we call this thing a row, and over here is a column, right? So when you need to read from DRAM, this whole row will be put into what we call sense amplifier. So the data will be put here. Why is it named sense amplifier? They are being amplified to sense what's in there. DRAM, as again, use the sense amplifier to amplify the data in a row, and only the data in the row buffer can be read. You can't just go directly into your chip, the DRAM chip, and read what's in that row. You need to bring that data into the sense amplifier or the row buffer. This is also called the row buffer. It's a buffer area for the rows of data. Okay? There are multiple operations to the row buffer. They can be open or that can be closed. An open row buffer, it means that there's some readable data from the DRAM row that are inside the row buffer. A closed row buffer means there's no data in there. Don't even try to read it, there's nothing in there. To close a row, to close from open to close, DRAM need to spend some time moving what's in the row buffer back to the DRAM row. Basically, you need to move that signals back to the original place. Why do you have to do that? Because again, there's only a few electrons. When you're reading this data, when you're done, move that back so that you can save the data. To read a row, to read the data, you must bring the row of data from your 2D array. Sorry. You might want to go get some water. Sorry. All right, I'm back. So to read the data from DRAM, you first need to bring the data to a row buffer. And there are three operations, basically. If you have an open row and you know that you want to read something from that row already, right? So this is what is happening. Let's say this is the DRAM cells. This is the row buffer. You want to read these green hash line from the row buffer, and it's already there. The only time you have to spend is, okay, I need to read that column, so I'm gonna go read that column in the row buffer. That's it. What do I have to do if I have a closed row and I need to read the data? Is this. First of all, you need to first move this row. Let's say it's row B. Move them to here. So that's the first step. Then you read the data, which is the second step. So with the green part, right? With the green part, oops, not green. If you have a data already in the open row, you only have to do one thing, which is the first step here. If you have a data, then you need to read it. It is not in the open row. You first need to do this, followed by this. So what happens if I have an open row, but then I need to read the data from an entirely different row, let's say row C. What happened in this case is you first need to write row B's data back. So that's the first step. Followed by the second step, move row C's data here, and then you read from this data right here. First step is move whatever is in the row buffer back. Second step is move whatever is in the target row that you want to read to the row buffer. And the third step is then you can read from the row buffer. You cannot read anything if they are not in the row buffer. Basically, the requirement is you need to put the data in the row buffer. Outside of these three cases, there are also other requirements that kind of govern DRAM timing. When you switch between read and write, or write to read, there are some certain time you have to wait until you can switch. There are also the refresh operation, which we'll cover in on Monday on what happens if I lose my charges. Right? Any questions so far? Any questions so far? So here are the basic operations and the time required to do this operation. When you need to read or write from DRAM, you need to wait. Inside the RAM spec sheet that you buy, you can look at this tool timing called CAS, column access stroke, or RCD, row to column. Read this time is the time that you are required to read the data that correspond to one cache line. It's a time when you have an open row, you know that's the row you want to read and you want to read that certain amount of data. Then there's another time called pre-charge. Pre-charge means that I'm going to prepare the row buffer to read the next row of data. This basically means that I'm going to move the current data in the row buffer back to DRAM. Move the current data in the row buffer back to DRAM. Oops, sorry. This is what I mean. So you have DRAM cells here, row B, for example. This is the time you have to move your data from row B back to the original DRAM location, right? Then there's also an activate time. Activate means that now that I have a closed row, right? Close. Activate means I'm going to move this row A into this closed row. So a normal sequence of DRAM is if you have an open row and you need to switch to another open row, pre-charge, activate, read, and write. Pre-charge can be done preemptively. If you know that you're finished with whatever is in that row, you can close it ahead of time so that when you need to read a different piece of data, you can just do activate and read writes. There's a latency switch that you need to do when you need to switch between read write or write to read basically and write to pre-charge. There's also amount of time to transfer data from DRAM chip across the bus to the cache. And if I look at the physical operation, I'm borrowing this from my friend's figure in his paper in 2015 because I don't want to redraw this. It's already been nicely drawn. Let's go through some physics. Do you know what's a capacitor? Okay, so can we only write data on the DRAM row? Yes. You need to write the data on the row buffer, and then you need to then pre-charge, move the data back to the row. So the way you write something to DRAM is this. Write that data, basically open the row, brings that row's data and onto the row buffer. Write that, move it back. That's why it takes a long time. That's why it takes a long time, right? This is also why it takes about 50 nanosecond instead of about 12 nanosecond here. You see that range of number I mentioned in the early day of this class, right? That say, okay, if you have to go to the main memory, it's ranging between 12 to 50 nanosecond. Sometimes it's 50 because you're reading something that's not in the row buffer. So you need to bring that thing in. If it's 12, it means I'm just reading from the row buffer. Does it answer your question? And I guess also, is it more clear now on why is there a variation on how long it takes to access data in DRAM? So here's a quick operation. So these cap dot stand for capacitor. Is a capacitor that store the cell's data. This is shared amongst all row in it's a thing called subarray. Subarray is basically a smaller unit inside the RAM bank. It shares this much bigger capacitor, and hopefully this bigger capacitor allows you to have more electrons so you can read from it. What will happen is originally everything is pre-charged. This stores the value 1, right? Because there are more electrons than half of my capacitor. I want to read from it. So I'm gonna go through a steps on what do I have to do if I want to read from it. The first thing I have to do, I'm going to close this gate. I'm going to close this gate, as you can see here. What will happen if I close the gate? What will happen? You have electrons here, right? This electron, which is greater than this value thing here, is half of VDD. VDD is some voltage value that is a reference voltage. It can be 1.5 volts, it can be 1 volt, it can be around 1.25 volts, depending on different technology. But it's a reference voltage. If it's greater than half of this value, you're dealing with the value 1. If it's lower than this, it's value of 0. That's how you can transfer binary information from electrons. Greater than half VDD, 1. Lower than half VDD, 0. So what happens if I connect the gate? Electrons from here will move into this capacitor, right? Because you close the gate, both of them will move until there's no voltage difference, so that both of them will be greater than half VDD. This thing start with half VDD, right? It means that during this step, right? During this step, you are essentially adding half VDD with some alpha. The alpha value comes from here, come from this capacitor into this alpha, right? So that bit line capacitor is now greater than half VDD. Everyone is with me so far? Basically, you close one gate, everything share the charges, they should have the same voltage. The same voltage should be greater than half VDD because my capacitor is greater than half VDD. Next step, are you guys with me so far? Or are you totally lost now? Okay, assuming that you kind of with me, if you have more questions, feel free to let me know. The next step, if I want to read something from it, I need to make sure I put this electrons, right? I need to make sure I put this electron to my sense amplifier, which is right here. That's a row buffer. The way I would do this is I'm going to close this gate. Close this gate. As you can see here, you close the gate. When you close the gate, right? When you close the gate, these sense amplification will amplify the signal, put the electrons in here. So once it reaches 3/4 VDD, over here will be 3/4 VDD, which means you can read from it and hopefully you can know, okay, that's a value 1. That's a value 1. Then the next step, now you finish reading the value. What I want to do next is to pre-charge, to close the row. To pre-charge, this thing would keep putting electron here, right? So that you finish the pre-charge process. Look at this. Everything here is at VDD. All the capacitor has fully charged with electrons. Once that's happened, I know I can open the gate. Right? I know I can open the gate. The original value of my capacitor is now fully charged, so I can afford for the capacitor to lose electron for a bit. Any question here so far? All right, so if there are no questions, I'm gonna wrap up today's class at this slides. And we'll continue on talking about DRAM and the memory scheduler in the next lecture on Monday. Any question before we leave?